Science time. Is this? Yeah, this is what I want. This is what I want. That's what I want. Okay. Oh, is the mic picking up? I didn't even check it. Okay, good. Today, classmates, scholars. Oh, the lights. Everything was not prepared. There we go. Now we're cooking with gas. Isn't that cute? Okay. Now we're cooking with gas. Today we are talking about one of the most fundamental qualities in all, not just of science, but of the universe. Can you guess what it is? You should already know based on your vocabulary. Energy, you got it. Energy. Also probably based on the objective, but we're talking about energy in general. Will you shut the doors, please? Thank you. Today we're talking about energy. Give me a definition from your own words, not one that you copied. So if you have a copied one, just don't speak. But from your own words, give me a definition of energy. Let's start a different way because I'm hearing a lack of responses. Tell me about your lab. Let's start with that. I saw at least 3 good labs yesterday. Tell me about your lab.
Good.
Let's try again. Tell me about your lab. I'm gonna do 2 things at once, and I'm gonna show you how I would diagram your lab when you tell me about it, which will 1 show you how to diagram a lab, and 2 that will help us talk about energy, which is what we're doing for our discussion. So start with your lab. What is your lab? I'm looking at some specific people because some people were here yesterday and did do the lab. Tell me about it right now. Okay, you weren't even here, Skylar. Let's hear it though. Imagine how Skylar is braver than all of you when she wasn't even here and she's still willing to do it. Let's hear it, Skylar. Oh, tell me about your lab. It wasn't a question, it was a statement. It was an imperative statement. Tell me about your lab.
My lab is a car slingshot.
Car slingshot. There we go. Okay. So if my lab was car slingshot, I would diagram car slingshot like this, and I would have the little car is here, right? And when you pulled back on the slingshot, what happened? It flew. It flew?
It drove away.
This is not a diagram. This is a drawing. To show that it's a diagram, I would label that this is I would put car. I would put that this, what did you use for your slingshot structure? Rubber band.
Clay and pink.
Rubber band. Oh, and it was held on with clay. Clay. Did they have to be pink, do you think?
Yes.
Okay. So that was one, and that's a diagram of one. Is this still recording? Is it still recording? Okay, it didn't. Okay. So we have that one. That's one diagram. I'm gonna because I've done science before. I'm gonna label that figure 1. Give me another example of a lab that wasn't Skylar's. Okay, Tally, who also wasn't here. Let the record show.
Measuring how hot tires get at the weight limit.
That's actually the one I was looking for. So we had in that one, we had a remote control car, right? It was actually a truck, and we put various amounts of weight in it. Weight. And then we drove it. And we measured the temperature. And it told us temperature. We measured the temperature of the tires, right? It's actually a good drawing. Actually, I take offense to actually. Give me another example. I want a third example of a lab, and then we're going to relate them all to energy. Justinian.
Our lab was the way of pole. We named it pole.
Okay. What'd you do?
So I run our RC car.
Okay, RC truck. Yes, forgive me. Yes, we had an RC truck.
What I did was grab a basket, some clay, for different sizes of clay, and string. Connected the string to the car, to the basket, put different sizes of clay into the basket, did each test on 1 by 1. Then I did a test on all 3 to see how it did, and it did well.
What was it? Just like towing them behind?
Yeah.
You had just lumps of clay in here? Clay. And you just, this is why you told me that you scuffed my floor, is because you were dragging a plastic basket along the nice wood floor. Okay, good. So we had the RC card. This time we did not have weight. And what were you measuring about your lab? You said it did good. That's not really a measurement. What were you measuring about it? I can tell your independent variable was how many clay you had, and you measured how fast? Okay. How fast? Question mark. Okay, so in each of these, what fundamental thing happened in each of these labs? We changed something, and we measured something, but what is it that we were changing? Okay, some of them changed weight. Yep, that's definitely true. What else? Some of them changed temperature. That's one thing that we measured. Some of them had a different distance. Yep. This one had a different distance or speed, right? Because we within a certain amount of time. And yep, we changed the type of string, and we got a different distance. And that's when we are talking. This is how fundamental energy is. When we're talking about what did you change in your lab and what changed because of it, energy. The definition I might have been looking for earlier is a way of discussing change. That's what energy is. Energy is a measurement. I shouldn't say a measurement. Energy is the quantity of change in the universe. The ability, we'll call it that, the ability to cause change. The ability to cause change. That's a very basic definition of energy. Your labs were to have met the objective model causes and effects of energy. Model causes and effects of energy. So I'm going to write that objective down, because hopefully by the end of this discussion, between the discussion and your lab, you will have met the objective. Sorry, we'll do more practice as we do the study guide. But what was the verb? I'm sorry. No, from the objective. Model. Here we go. Model, cause, and effect of energy. So, what caused a change in these labs? What was the cause in this lab? What was the cause of the change? Okay, so we had to have some motion to begin with. What was the cause? Let me phrase it this way. Maybe we should start with the effect. What was the effect of energy in this lab? What was the effect it had? Come on, you guys, I know you can think. I'm aware it's the afternoon, but you probably can think. And maybe you didn't all see Mason's lab, but what was the effect? Do you know what the word effect means? Effect means like what happened because of it. So what was the effect? What happened in Mason's lab? The car went forward, okay? Car went forward. What was the cause of that?
The system?
Yeah? What part of it, or what happened?
The slingshot?
Slingshot, yeah. The slingshot was what? The slingshot was, yeah, it did propel, but what did Mason do that caused the car to go forward? The slingshot was, I'm looking for a verb here, pulled back. Very good. You're a real scientist. So because the slingshot was pulled back, the car went forward. That's a change, right? So we know the energy was involved in that somehow. What about in this one? Again, we'll start with the effect because that seemed to be easier for you. Tire got hot. Why?
Because the weight being added.
Did the weight being added make it might have made it get hotter, but what made it get hot at all? Yeah, the movement. Because the car was moving, the tire got hot. I have been forgetting to do my good penmanship. I'm sorry. In this one, what was the effect? So the cause was probably, I hear discussion about the way, the different weights, right? The car pulling the different weights. Pulling weight caused what? Change in, yep, good. Change in speed. So do you see that all of these involve a change? I mean, that's almost a futile question because everything in your life involves change. You can't not have change, but all change requires energy. That's how fundamental energy, the discussion of energy is to science, is that all change is caused by energy. So we talk about several different kinds of energy. In this one, I'm going to do a different color. In this lab, what kind of energy were we supplying? You know, you probably should. You have a list of energies that you had vocab words of, right? Your vocab words had a list of energy. So no, that wasn't the cause. We did what? We added what to the system? When we pulled this back, we were giving it what? One of your vocab words. What kind of potential? You're right. So it was going. What kind of potential, though? What kind of potential energy? Look at your list. Look at your list of vocab words. What kind of potential energy did we add to the system by pulling back the rubber band? Okay, that's right. When we were holding it, we were adding potential energy, and then when we released it, it changed to kinetic energy. But I'm still looking for what kind of potential energy did we add to the system? Do you have your vocab list? Does anyone have a vocab list? Oh, it isn't one of them. No wonder you can't get it. I'm looking for, and you should write this down, elastic potential energy. Have you heard of the word elastic? I think if you have done your study guide at all, this is one of the first things discussed in there is the kinds of potential energy. Have you heard of elastic? What does the word elastic mean? And give me an example. Stretchy. Yep. Give me an example. Is anyone wearing? Nope. Is anyone wearing something elastic? You absolutely are. Every single one of you on somewhere on your body is wearing something elastic. I guarantee it. But the elastic means it's stretchy, basically. So that energy is stored as stretchiness. I have one right here. Boop. I got this from VBS. But look, if I pull it back, it's storing energy, and then you already know what's going to happen if I let it go. Ava's flinching already. I haven't done anything yet. But if I let it go, it has kinetic energy, right? That energy changes from elastic potential energy to kinetic energy. That energy changes from elastic potential energy to kinetic energy. And this is the first of the actual things we're going to discuss today, which is that this is called an energy transformation. That's one of your vocab words too. Energy transformation. What's the word transform mean? I feel like I'm making you define a lot of words. Change. Yeah, well, it's another kind of change. But transform means change form. Transform, trans means across, form means form, or form means shape. So it's changing from one shape, metaphorically, one shape of energy, one type of energy to another. So it was elastic potential energy. We gave it elastic potential energy by pulling it back, and it became kinetic energy. It became energy of movement. Okay, and what about this one? Well, we know there's going to be an energy transformation here too. It was movement, right? We can start one step earlier. What caused the tires to move of this car? The power. Of what? What's in there that caused it? The motors, yes, okay. So motors change electric energy to movement. That's what a motor does. Where did that electric energy come from? No, they manifest their own energy. That would be crazy. Batteries. The batteries are chemical energy, which is another kind of potential energy. You should write that down. Chemical energy is a kind of potential energy. What has chemical potential energy? The example we just gave? Batteries. What else? Can you guess? What else has chemical potential energy?
Tesla.
Yeah, because they have batteries. What did you have for lunch? Hot dog, and you had a fruit salad or fruit snack. That's not really surprising to me at all. Yes, a hot dog has chemical potential energy. That's exactly right. The food you eat, I don't know. You guys think probably that it's just a miracle that you eat and then you can move, and it is a miracle in one sense. But what's happening is that the food you eat has chemical potential energy, and what your body does is change that chemical potential energy into kinetic energy, electrical energy in your nerves. It changes it to heat energy. That's why you're warm. But your body changes that chemical food. Hey, and guess what? How you know that's true? If you stopped eating, what would eventually happen? You die. You wouldn't be able to cause change anymore in the universe because you wouldn't have enough energy. So the chemical potential energy in your food or in the battery, in the case of this car, it changed to electrical energy. In the case of you, it changes to electrical energy in your nerve impulses, and then that is provided to your muscles, which then, like the car, changes to kinetic energy, movement. And in all of those cases, the tire gets hot. This is a very interesting energy transformation called friction. You remember we talked about friction. We talked about friction in the sense of it has the ability to resist motion. In the last lesson, we talked about how friction can resist motion. But now you also need to know that friction causes kinetic energy to become thermal energy. That's what friction does. So kinetic energy, movement, have you ever done this? If it's cold, what's that make your hands feel like? A little warmer. And that's because you're moving them and they're rubbing, and that friction causes thermal energy. So the energy transformation of kinetic energy, whoops, I want to use an even different color, of kinetic energy to thermal energy is called friction. And in some cases, this is nice. In some cases, this is what we want. But you remember from our discussion about forces that this also slows the car down, right? As the tires get hotter, it also means the car is going, right? It's removing kinetic energy from the equation, and so it's going slower. You remember the thing about in Newton's first law says that, oh, there was a screw there, come to find out. Newton's first law says that an object in motion stays in motion unless acted upon by an outside force. And so according to Newton's first law, this should roll forever. But why doesn't it? Friction. And so in the sense that it causes thermal energy, sometimes that's good. Sometimes that's good. But a lot of times that causes a decrease in what we call efficiency. Efficiency is the measure of how much energy goes out divided by the energy that goes in. So the energy provided to a system divided into how much energy goes out. And guess what? It can never be 100%. There's always going to be some lost to heat. We use that phrase lost because the energy is no longer usable once it's thermal energy. Or at least it's not usable in the same way. Okay, and then lastly, this one. It's pulling weight and it's changing its speed. So this again was friction, right? This one was measuring also friction. And we were increasing friction by adding more weight because friction, you don't have to know this equation, but the force of friction depends on the normal force and what's called the coefficient of friction. So the rougher things just have a higher coefficient of friction, period. But we can also increase friction by adding the normal force, which means that like if we basically, in our hand example, if you press harder, you'll get more friction. Even though you're not changing how rough the surfaces are, if you press harder, you get more friction. So if you press very gently and go the same speed and then you press harder, you'll get more friction when they're pressed together harder. So basically, the harder they're pressed together and the rougher they are, the more friction there is. Will you get more friction if you are sliding your little socks on carpet or if you are sliding your socks on a bare floor?
Bare floor.
No, more friction on carpet or on bare floor? Carpet because it's rougher. Some other kinds of energy that we didn't mention, and if you were here yesterday, because of Justinian's really big RC car, you would know that there was also sound energy produced. So sound